So which way is it becoming more metallic? Somebody draw it on my screen. Or do I get to pick someone? So do I have a volunteer or does somebody have to be voluntold?
Is it left to right? Because I'm reading in all the alkaline metals. Just start from there.
So you said left to right?
Or no, right to left.
Right to left. So it becomes more metallic in this direction?
Yes.
Okay. Okay, that's true. And then what about from top to bottom?
Becomes more metallic from top to bottom.
So from top to bottom, it becomes more metallic?
Yes.
Okay. That is also correct. Okay, what about ionization energy? What is ionization energy?
Like, where does it start? I know it starts from left to right, and it just.
So the ionization,
explain it.
Ionization energy, what you said from left to right?
Yes.
So you're saying it increases from left to right?
Yes, and it increases from bottom to top.
Okay. What is ionization energy?
Is ionization energy the removing of an electron?
The removing of an electron, yes. So the energy that is required to remove an electron. So who's going to have the highest ionization energy of all of the elements? Who's going to have the lowest, one of the lowest ionization energy of all of them? Anyone?
Oh, which ones are going to have the highest removing?
Which element on the periodic table is going to have the highest ionization energy, and which one's going to have the lowest ionization energy?
Is francium the highest?
What was that?
The highest would be helium.
The highest would be helium. Now, you got to think about it. It's the energy that's going to be required to remove an electron, right? And so who's going to have a very low ionization? So we know that the alkali metals want to lose an electron, right? So their energy is going to be pretty low. Where our noble gases, they do not want to lose an electron. They're like, we're stable, we're happy the way we are, don't mess with us, right? So they're going to have a very high energy. They're going to fight you more for that electron than something like francium, right? Does that make sense?
Yes.
Okay. What about electron affinity? Electron affinity is the desire to gain an electron. Who's going to want to gain an electron? Who's going to want it more than anyone else?
Would that be the highest on the ionization table or the ionization chart?
So yes, the one that's going to be, well, it won't be the highest because noble gases are the highest. But do noble gases want to gain an electron?
No.
No. But who really, really wants to gain an electron?
Elements like nitrogen, oxygen, and fluorine and chlorine.
Okay, so those guys want to gain electrons. Who wants to gain it more so than anyone else? who's so
Chlorine.
close to being a noble gas that they're going to do just about anything to get that one electron that they need. Which family?
The reactive nonmetals.
Okay, which one is that? What are they called? Look up, you have the periodic table in front of you.
The nonmetals.
So they're going to be nonmetals, yes. So nonmetals, all are going to want to gain electrons. That's true. But who's going to want to, out of all of the nonmetals, which family is going to want to gain more than anything else? Which family?
The noble gases,
The noble gases. Good job. Who is that? High five.
me,
Who is me?
Leticia.
Good job. So the noble gases are going to be, they're going to like, hey, I am one away. I really, really, really want that electron. Right? So they're going to have the highest electron affinity, right? And then, of course, the little tyrant itself, fluorine, is going to have the highest of them all because it's really hungry for that one electron compared to the other noble gases. I mean, the other halogens. Okay. Okay, so are you guys feeling that so far? Makes sense? Not too hard? You see those trends? Good. Okay, so let's get on started on chapter 12. Chapter 12 is quick, simple, and beautiful. Okay, so we've already talked about ions, right? So a cation is what?
Positive charges.
Positive charged ion. Okay, and an anion is what?
Negatively charged ion.
Okay, so how does an element become a cation?
By taking away the electrons.
So by losing an electron, right? So you're right, taking away. So giving it away, losing it. Okay. How does an element become an anion?
It gains one or more electrons.
Okay. So it gains one or more electrons. Simple, not too hard. Okay. So which family wants to become cations? Now pull up our periodic table. Sorry, I didn't get a chance to eat lunch, so I'm munching on some jerky between.
The metal family.
So metals, almost all metals are going to want to become a cation, right? So who's going to want to become anions?
The nonmetals.
The nonmetals, okay? Except for which group of nonmetals don't want to?
Noble gases.
Okay, got it. Okay, so you guys can see my screen, right?
Yeah.
Yes.
Okay, so like, for instance, we have nitrogen. We know that nitrogen has 5 valence electrons. If nitrogen wants to become like the noble gases, how many electrons does it need to get? Here's nitrogen. It has 5 valence electrons, 1, 2, 3, 4, 5. For it to become a noble gas, how many more electrons does it need to have?
3.
3.
3. 1, 2, 3. So it's going to want to try to get 3 more, right? But if we drew the Lewis dot structure of nitrogen, how many dots does nitrogen have around it?
7.
How many
5?
It has 5 because remember, although nitrogen has a total of 7 electrons, it only has 5 valence electrons. What are valence electrons? We've talked about this before.
It's electrons in the outermost ring.
Okay, and what does that mean? So you're right, it's the electrons that are in the outermost range. But what does it mean? What do we care about that? Why do we care they're in the outermost range?
Is it to fill the octet rule? Like it's
Okay, so it has to fill the octet rule. You're getting a little bit closer. For what? So what? Why do we care about those electrons? Why are they so important? What is the goal of every element except for noble gases?
is it to be like stable?
To be stable, right? So how do you become stable?
Filling the ring with 8 electrons.
Okay, filling the ring with 8. So you're like the noble gases, right? Okay, and how can you do that? How can you fill that ring with 8? What ways? Okay, can I ask you a question? How many of you guys are poor? Raise your hand
Me.
if you're poor. Anybody independent, wealthy? Has everything they ever wanted in life? Anybody? Come on, speak up, speak up, speak up. I want to know. No.
Poor, but I'm okay.
Well, you're not poor, but you're okay?
Yeah.
Okay, okay. Well, I'm poor. I recognize it. I can acknowledge it. I'm poor, right? I financially, it's like I'm working towards stability, right? So part of the reason I'm working towards stability, right? So if you're thinking about it and you're poor, what are ways that you could become stable or wealthy?
Work a second job. Be a little more financially responsible.
Okay,
Use those coupons you get in the mail.
use the coupons you get in the mail. Okay. Any other ways?
You either invest or
Okay,
Bring in more money.
Manage.
you can bring in more money, manage, work more jobs. Any easier ways?
well, there's a lot of easier ways, but are we able to discuss those?
Okay, wait. There are a lot of easier ways, right? So a couple of ways that you guys could do it, right? Let's say I was a really wealthy prince, right? Or king. And I come to you, Letitia, since you're responding with me. And I say, Letitia, you make me smile. I love your energy. You're so bubbly and you're glowy. I want you in my life always. Will you be my wife? We don't have to have sex. We don't have to do anything. We could just share each other's company,
Mhm.
and you get half of my kingdom, half my money, half my riches, my pain, my dough. What would you do?
Well, first of all, I guess we'll discuss if there is anything that I can't do besides, supposedly we will not have any contact. We would just be living together. But I forgot the terminology I'm looking for. Any terms.
Okay, so we got terms to our proposals. That's what you're telling me. In other words, if I agree to all your terms and all of that, you'd be like what?
Well, I don't see why wouldn't I you know, I benefit from it, you benefit from it. Why not?
Okay. So we got it right there. Some mutual benefit that comes from it, right?
Yes.
I have something that you want. You have something I want, right? So then we can share that concept, right? So we can share those, in a sense, share those electrons, right? Being my task, right? So I have an extra one. You may have something that you're a little short on. So by us sharing together, we can be more stable, right? So a lot of times that we make our decisions, our life decisions about stability, right?
Yes.
Okay, so that's what's going to happen in the case of these atoms as well, too. They're looking to find ways of being stable. There are basically a couple of ways that you can do it. One, you can share electrons, right? And sharing could be, you know, there's a lot of ways to share. We'll talk about that here in a second. Or we can take and give electrons, right? So the reason why those valence electrons are so important, because those are the electrons that are going to be negotiated, that are going to be used, right? So either you're going to be taking those electrons, or you're going to be giving electrons to kind of fill in those empty spots that are available, right? So valence electrons are important for bonding, okay? You guys got that?
Yes.
So they're really, really important for bonding. And so it's really important that you guys understand how many valence electrons we have, okay? So aluminum, how many valence electrons do we have for aluminum?
Three.
We have 3 valence electrons. So aluminum has the opportunity to either lose 3 electrons or to try to gain 1, 2, 3, 4, 5, 6. Or try to gain 6 electrons. What is it going to want to do? Think about it. If somebody says you could either mow 3 lawns or you can mow 6 lawns, sorry, 5 lawns, not 6. 5 lawns, what are you going to do?
Do the 3.
Yeah, let's say, assuming you get paid the same. You're going to do the easiest one, right? So aluminum, again, wants to become a cation because it's easier for it to lose those electrons. And so somebody's going to ask me, well, does it just throw them away and that's it? Well, no, it doesn't really just throw them away. It reacts with something, right? So there's some bartering that goes on. 3 electrons are going to be given to somebody, let's say fluorine, right? Fluorine only needs 1 of those electrons. But if you have 3 fluorines and you give 1 of them, give 1 here, we give 1 here, and we give 1 here, that makes fluorine happy, right? And so these guys would come together and they would form what we call an ionic bond, where it's based upon charge. Fluorine has a negative charge, so there's 3 fluorines that are going to be needed for it to balance out that 3 positive charge of aluminum. Are you guys with me? So aluminum gives up its electrons so that fluorine can gain its electrons. So it's kind of like a bartering system, right? You give up and I take. And because they're opposite charges, positive and negative, they come together. They form an ionic compound. Does that make sense? Aaron, you have that look? Okay, good. So we have nitrogen, who has 5 valence electrons. We know that if nitrogen gets 3 more electrons, it's going to be good to go. let's say nitrogen and magnesium are going to be coming together. How many electrons does magnesium have? How many valence electrons does magnesium have?
2.
It has 2. Okay. So since magnesium has 2 valence electrons, right? What do you think it wants to do? Does it want to, because it wants to be like a noble gas. It's here. If it loses its 2, 1, 2, it becomes like neon. So if it loses these electrons, it becomes like neon. So what is it going to want to do?
Try to take away the electrons away from the nitrogen, since it wants to become more of a cation instead of an anion.
So is it going to want to take these electrons? Because it could lose 2, or it could try to gain 1, 2, 3, 4, 5, 6 to be like argon. So it has right now, if it loses 2, it could be like neon, or it has to gain 6 to be like argon, which is going to be harder work.
It's going to work smarter, not harder.
Work smarter, not harder. Exactly. So in that case, it's going to want to get rid of those 2, right? So if it gets rid of the 2, it becomes Mg 2+ with no dots, right? So the way that we typically write this, if we're talking about an ion, such a fluid structure, okay, so that's magnesium 2+. So nitrogen needs a total of 3 more. So we have 2 electrons that are sitting here for it to use. We need to figure out a way that nitrogen can get what it needs, right? So in this case, if we have 3 magnesiums, all of them that are 2+, and we're just going to put these dots here on the outside. That'll be a total of 6 electrons, right? We know nitrogen needs 3 to be like reach its octet. So we're going to need 2 nitrogens to take up these electrons. So in this case, when nitrogen gets those electrons, here are the electrons. They're going to be transferred to nitrogen. Each of those nitrogens are going to be 3-. We have this together, 3- times 2. So 2 times -3 is what?
-6.
And then 3 times +2.
6.
So these guys can come together to form an ionic compound and balance each other out by having 3 magnesiums and 2 nitrogens. Okay, you guys can you see it? Because the overall charge on this guy would be 6 plus 6. The overall charge on this guy would be -6. So they have to balance each other out numerically. Does that make sense?
Yeah.
Okay. Okay, so again, these electrons are going to be given. They're going to either be given away, or I should say, some of them are going to be taken, some of them are going to be given. Okay, so the metals are going to want to get rid of their electrons to be like a noble gas. And the non-metals are going to want to gain electrons to be like a noble gas. And because they're opposite charges, they're going to come together. Okay? Because opposites attract, right? Are you with me? Okay, I take that as a maybe. Okay, so let's take a step back then, right? So these are all nonmetals, right? All of these nonmetals, we know that nitrogen has 7 electrons. Of those 7 electrons, only 5 of them are valence electrons, because we know that this guy is the same thing as helium. It's in that core. So these guys are the only ones that we can use for reacting, okay? So for us to reach our octet, having 8 around us, we would have to gain 3 electrons. So if we gain 3 electrons, then we're going to be like a noble gas. And then our outer shell is completely full. So we're going to be just like neon. Okay. Let's see, make sure I'm not lying to you here. Okay, so we have nitrogen, 1, 2, 3, just like neon, right? If it gains 3 electrons. Oxygen. Oxygen has a total of 8 electrons, but only 6 of them are going to be valence, right? So then if we look at it, we look at our valence electrons. These guys are our valent electrons, 6. So it needs 2 more to be like neon, right? So then if it gets its 2 more, then it becomes O2 minus, right? And it's happy, okay? Fluorine. Fluorine is 1 away from being a noble gas. So it has 7 electrons around it. It needs that 1 extra electron. It gets that 1 extra electron. It becomes F minus, and it's just like neon, okay? Now, the term, and it says it up here, isoelectronic. Isoelectronic basically means that you have the same number of electrons as, let's say, a noble gas, or as some other element, exactly the same number of another element. So when you form ions, your goal is, in the case of these ions specifically, they're looking to try to be like neon. So they're going to have the same number of electrons as neon, because neon is stable. Their goal is to try to have a total of 8 electrons in the outer shell, or 8 valence electrons around it, so that it's just like neon. Okay. So again, that term isoelectronic basically means the same number of electrons. Iso meaning same, electronic, electrons. Okay. So on the other end, we have these cations, or we have these metals that will form cations. So we have sodium. Sodium has 1 valence electron. So since sodium has 1 valence electron, if it loses that 1 electron, it becomes just like neon. We have magnesium. If magnesium loses 2 electrons, it becomes just like neon. If aluminum loses 3 electrons, it becomes just like neon. So all of those guys are considered to be isoelectronic to neon, or with neon, because it's looking to be just like neon. In that case, the same number of electrons. Does that make sense? Anyone? Kind of. Okay. So I'm going to ask you a question. Get this to behave. Okay, so we have argon here, right? So how many electrons must silicon gain to become isoelectronic to argon?
4.
It needs to gain 4. So Right now, how many valence electrons does silicon has? Normally,
3. No, 4.
Is it
Four.
4?
it has 4. 2, 3, 4. So if silicon gains another 4, what is going to be the charge on the silicon? Ion.
Negative?
Negative what?
Negative
4.
4?
That's right. So we write it as 4 negative, right? We can also write it in terms of the Lewis structure as 4 negative. Okay. So this guy has the same number of electrons as argon. What about sulfur? How many valence electrons?
6.
How many does it need to gain to be like argon?
2.
2?
So what will be the charge on it?
2 negative.
Okay, negative what?
Negative 6.
2.
Ooh.
Wait.
How many
Negative.
electrons did it gain?
2.
2. We know that each electron is negative, right? So when you're an element on the periodic table and you don't have any extra electrons, you're at 0. If you gain electrons, you become negative. If you lose electrons, you become what?
Positive.
Positive.
Positive. Okay, so let's look over here. If we have calcium, what is the Lewis dot structure of calcium?
Is it just 2 dots?
Ca with 2 dots. Okay, so for it to be like argon, what does it need to do?
It needs to lose 2 valence electrons.
Okay, so if it loses 2 valence electrons, what is going to be its charge?
Positive 2?
Okay, so we just draw it like this, or we'd write it just normally like this, Ca 2 plus. Okay, so then that guy would be isoelectronic to argon. Does that make sense?
Yeah.
Okay, so when we make that term isoelectronic, it just basically means it has the same number of electrons, right, as something else, right? Exactly the same number of electrons as something else. Okay, now ions do this to try to be like noble gases, right? So they're going to do what they want to do to try to get like those noble gases. Does that make sense?
Yeah.
Okay, and again, they're going to do that either by giving up electrons or by gaining electrons or by sharing electrons. Okay. Okay, so this is just basically showing you, you can see the ones that are in the same colors that are isoelectronic to each other. Like say, for instance, lithium, it's isoelectronic to helium, right? Sodium plus, isoelectronic to neon. So the ones in blue are all going to be isoelectronic to this noble gas. Okay, makes sense? Not too hard?
Makes sense.
Good. Okay, so write the electron configuration for the calcium ion. So this time we're writing the electron configuration. So what would be our electron configuration for calcium? And then we'll do the ion. So Ca, electron configuration for Ca. So what's my core?
Would it be argon?
Okay, and then, so we're starting here.
Then it would be 4s2.
Okay, so it'll be argon 4s2. Now, if I was writing the electron configuration for the calcium ion, we know that the calcium ion, it's in the second group, it's 2 away from being a noble gas, so it's going to lose those 2. So we know it's going to have a 2+ associated with it. So what would be the electron configuration for that guy? Two plus means what? Let's see.
Subtract 2, right?
Subtract 2 of what?
Electrons.
2 electrons. So if I'm
Yeah.
removing 2 electrons, where am I removing them from? Am I going to break open my core?
No.
No.
No. So I'm just going to have my core, and then these guys, we're going to take it from here, 2 electrons right there. Okay. So that just shows me that calcium 2+ is isoelectronic to argon, because argon is my core. It has all the same number of electrons as argon. Do you get it?
Yeah.
Okay. So this is writing it the long way. Here, again, you're getting rid of that when you're losing 2 electrons. That 2 represents the number of electrons. Good, bad, or ugly? Okay, so we talked about ionic bonds, right? So ionic bonds are just opposite charges that are coming together to form ionic compounds. Now, the rules for ionic bonds is, or ionic compounds, is that they have to balance each other out. So we had calcium earlier, right? So if calcium is going to be 2+, and fluorine, what is going to be the charge on fluorine again? Anyone?
I think that would be a minus. Oh,
That
well.
is correct, Mary. It is going to be a minus because
Oh,
it's 1 away
correct.
from being a noble gas, right?
Yeah.
So it wants that 1 electron. So it's going to take that 1
Yeah.
electron. Okay, so how many fluorines will I need to balance out that +2 charge on calcium?
You need 2 fluorines.
I'll need 2 fluorines. So I have 2 fluorines here. Both of them are going to have a negative charge. So that's
Yeah.
1, -1, -2. That balances out that +2. When I write this chemical formula, this guy would be CaF2.
F2.
And because it does not have a total charge, we don't put any charges up here because we're balancing out those charges. Okay? So ionic compounds will balance the charges out. Do you guys see that? Yes, no, maybe?
Yeah, I kind of see it.
See.
Okay, so let's try another one. Let's say we have, let's see. Let's say we have oxygen. And we have sodium. Okay, so sodium is going to be what charge?
Plus. Plus.
Sodium is going to be plus?
Yeah.
Okay, Alan, what's going to be the charge on oxygen?
Or oxygen?
Yep.
Would it be? Let me see. Oxygen with 3-.
Would it be a 3-? How far is it away from being a noble gas? How many?
Oh,
electrons?
2.
It needs
2-.
2. So then it's going to have a 2-. Okay. So how many sodiums am I going to need to balance out that 2-? If each one is only worth 1+.
I'm gonna need two
I'm
two
gonna,
sodiums.
so then my compound is going to be Na2. Oh, do you guys get that?
Yeah.
It's just simple math, right?
Mhm.
Okay, Tucker. Are you there?
Yeah.
Okay, Tucker. Okay, so here's the question. So I have aluminum. And let's see. Let's do phosphorus. Okay. So aluminum, what ion is aluminum gonna form?
They say is it we're gonna what?
What ion is aluminum gonna form? Let's look at the periodic table. Here's aluminum. What ion is it gonna form? Aluminum. What does it have to do to become a noble gas?
Would it have to be a negative? Like negative?
Would it be a negative? Is it easier? Think about it. If you add electrons, it becomes
Oh,
negative.
you have to, yeah, it's easier to, I think, be plus.
Okay, plus what?
+3.
Plus 3. Why plus 3? Are you there? Did I lose you?
Sorry, because it's easier to be a noble gas if you add electrons
If I add electrons or lose electrons?
or lose electrons.
Okay, if I lose electrons. So I'm here at aluminum, right? So if I lose 1, 2, 3, then I become neon, right? So that's going to give me my charge. The fact that I lost 3 electrons, that's going to give me my charge. Okay, now phosphorus. Phosphorus is P. Okay, here's phosphorus. Put it in blue. Can you guys see that? You see where phosphorus is at?
Yeah.
Okay, so what is phosphorus going to want to do? Is it going to want to lose electrons or is it going to want to gain electrons?
Is it lose electrons?
Okay, if it loses electrons, it needs to lose 1, 2, 3, 4, 5. Compared to if it gains electrons, 1, 2, 3.
So that would be 3 negative.
3 negatives. Okay. So we have phosphorus 3 negative. I'm just going to write this in blue. And we have aluminum 3 positive. These guys balance each other out perfectly. So then the ionic compound is going to be AlP. Okay.
Wait, why did you go 3 negative?
Because you're gaining electrons, right?
Yeah.
What is the charge on electrons? Is electrons negative or positive?
Negative.
It's negative. And that's what we got to remember. Electrons are negative. So anytime that you add electrons to something, that thing is going to become negative. Okay? Anytime you remove electrons, it's going to become positive because that means that you have more protons than you have electrons.
Oh, so because you subtracted electrons from aluminum, you have to add. Is that right?
Yeah.
No, it's not because you have to add. Because you subtracted electrons from aluminum, aluminum still has how many? Let's say like, so if we have aluminum 3 plus, how many electrons does aluminum 3 plus have? You just told me that it lost 3 electrons. So how many
10?
does it normally have?
13.
It normally has 13. Now we just lost 3, then it's what?
10.
So we have 10 electrons. Okay. How many protons? We know that protons are positively charged.
Would it be 13?
It's going to be 13, right? Our protons are never going to change. That's what defines our element.
Okay, I see. I see. I see.
Okay.
What you're saying.
Because this guy is negative and this guy is positive, we have more positive, so the charge on it is going to be +3. Make sense?
Yeah, I see that. Yeah.
Dr. Henry,
Yes.
for the ionic compound overall for aluminum and phosphorus, you didn't have to put a 3, right? Since they balanced out?
That's right.
Oh, okay.
And again, +3, -3, that's going to equal 0 if you add them together, right?
Right.
And our goal is so that our compound is stable.
Oh,
It has
okay.
a 0 charge on it.
Oh, okay, I see.
Okay. You want to try one more?
Yeah.
Yep.
Okay, so let's see. Selenium and lithium, Li. Okay, so lithium, what's going to be the charge on the lithium ion?
Would it be +1?
Okay, so it'll be Li plus. And then what about selenium? Where's selenium? What group is it in?
16?
In group 16. What period?
4. Here.
Or
4. Okay. So what's going to be the charge on selenium when it forms an ion?
would it be -2?
Okay. So we have lithium, that's +1, and we have selenium, who is -2. So how many lithiums are we going to need to have to balance out those selenium?
2 lithium?
Okay. So it's Li2 Se. Okay. Simple.
What's the compound? What is it called? What is the compound called?
It's called lithium selenide.
Okay.
We'll talk about nomenclature later. So
Okay.
don't get ahead of the game yet. Okay. So
Yeah.
this is an ionic bond, right? Ionic bonds occurs between metals and nonmetals. I'll repeat that. Ionic bonds occurs between metals and nonmetals. Let me type it out too. Ionic bonds between metals and nonmetals. Okay. And I should say, for the most part, because there's always going to be an exception. And I'll show you an exception a little bit later. Okay, so are you guys with me so far? These guys are called monoatomic ions. They're called monatomic ions because there's only one atom involved. It's only one atom. It's lithium, right? This guy's selenium. So those are both ions. This guy's called an ionic compound. That's when you have your ions coming together. So is lithium a cation or an anion?
Cation.
Okay. And selenium must be the
Anion.
okay. Okay. Okay, so let's go back to the slides now that you guys are all with me. Okay, so nearly all ionic compounds are going to be solids. Almost all of them are going to be solids at room temperature and standard pressure. And these solids are going to form what we call crystal lattices, right? So they're going to have a geometric shape that's going to be associated with them, and they're going to kind of organize themselves in a certain way. And I'll show you that a little bit later. Okay, ionic compounds, at the end of the day, they have to have a neutral charge. In other words, they have to add up to 0. That positive and that negative at the end has to add up to a total of 0. When they're in water, they conduct electricity really good. But when they're not in water, they don't conduct electricity. Okay? For ionic compounds in solution, in the water solution, is going to conduct electricity, where when they're not in an ionic solution, they won't conduct electricity. Also, the bond is pretty strong. So that attraction is really, really, really strong. Okay? And that's also part of the reason why they're solids at room temperature, because they're really attracted to each other. And they're playing on those positive and negative charges. So they're interacting with, let's say you have a positive here, you have a negative here, you have a positive here, you have a negative here, you have a positive here. And I'll show you that. It'll make more sense once you see it. You'll be like, oh, I get it. Okay. So here's an example where we have sodium metal and chlorine gas. And you see both of these guys are very, very reactive. So when they get in contact with each other, they're like, ooh, it's like heaven. It's like, chemistry really takes place, right? Because sodium wants to get rid of that 1 electron and chlorine wants to get that 1 electron, right? So sodium was like, hey, here, you have it. And then chlorine's like, yeah, finally. And then they're like, one is positive, one is negative. So they come together. Oh, it's like a cute little relationship, They come together really tight, okay? So let's see what that looks like in terms of a structure. So here we have sodium. Sodium has that 1 extra electron. So what it does, it gives that 1 electron to the chlorine, okay? Chlorine has 17, right? It needs to get that 1 more, or it has 7 valence electrons. It needs 1 more to have that 8, right?
Yeah.
So it's anxious. It's like, oh, and then so when they meet, it's like a match made in heaven.
Mm-hmm.
Okay, so then they come together to form sodium chloride. You guys know what sodium chloride is, right?
Yeah.
Does it kill you?
No.
Well, it can, right? If you have too much of it.
If you want to explode, then yeah.
What was that?
If you want to explode, then that's up to you.
Well, sodium chloride? What
Yeah.
is sodium chloride?
Huh?
What is sodium chloride?
Sodium chloride?
Yeah, chloride. We have it.
Isn't it salt?
It's salt. That's right.
Salt
It
mixed
is
with
salt.
chlorine.
Right? Sodium chloride is salt, right? And so,
Yeah.
but we know that chlorine is very volatile, and we know that sodium is very volatile. So this kind of helps us understand that when you put these guys together, it allows them to be stable. When they're by themselves, when sodium is all by itself, ooh, it's a hot mess, right? It's
Yeah.
anxious, like, oh God, I have that extra electron, got to get rid of it. Chlorine is the same way. It's like, man, I really need that 1 electron. It is a hot mess. When you put it together to form an ionic compound, we get salt. Does salt kill you when you eat it? Well, if you don't eat too much of it, does it kill you?
No.
Right? It doesn't, right? You guys, I know you put a lot of salt on your food. Do you not put salt on your food?
Sometimes.
I'm eating jerky here. It's full of salt. Put a little salt on your mashed potatoes. You guys do that?
Yeah.
You put salt in your butter when you make butter, salted butter, right?
That's just unhealthy.
But it's delicious, right?
You.
Okay. So if you guys look on the screen, right? Over here, you have the chlorine molecule is going to be the green. The sodium molecule, or the sodium ion, the chloride ion is going to be green. The sodium ion is going to be black or gray, okay? And you see that it's alternating. So that's what the salt structure looks like on an atomic level, right? So you're just having alternation between the two. And it's all based upon charge. We know that sodium has a plus charge. Chlorine has a minus charge. So you have sodium, positive, positive, negative, positive, negative, positive, negative. And you form these crystal lattices. Do you guys see that?
Yeah.
Good. Okay, so this is just another structure of showing you exactly the same thing. Our lattice structure forming. This basically shows you that It's able to conduct electricity when it's in its liquid state. And that's because of those charges, right? Because sodium is positive, chloride is negative. And so when you put it in a solution, you have positive and negative charges in there. And so, and electricity is just electrons that are flowing, right? You guys know that, right?
Yeah.
Well, you know it now, right? Okay. So are you guys with me?
Yeah.
With me so far? Okay.
Yeah.
So that helps me understand about ionic bonds, right? So let's talk about covalent bonds. So ionic bonds were just about giving and taking. Covalent bonds are about sharing. So you're sharing electrons between two atoms. Now, nonmetals share with nonmetals. I often use this analogy. I know there are no criminals in my class. You guys are the best students ever. Most honest, upstanding citizens ever.
Yeah.
But let's say you were a criminal, right? Or you had a criminal mind. And your neighbor had this really cool bicycle or a motorcycle or car, right?
Okay.
Some motor transportation. It is the nicest car ever, right?
Yeah.
Now, your neighbor has this rare car, and in the town, 100 miles away, somebody else has this car, right? Now, if you were a criminal and you had a criminal mind, would you steal from your neighbor that car from your neighbor? Or would you steal that car from that person that was in a town 100 miles away?
Yeah.
The
The
person
pop.
who's out of town.
Yeah.
It depends who's out of town.
No, the person out of town.
No, the person out of town. Okay, why would you do that? Why would you steal from your neighbor?
Because you won't be
Because
If you steal from your neighbor, you're going to get caught because where are you going to keep the car and where are you going to drive it? Like,
Yeah, exactly, right? So if you steal it from your neighbor is right there, right?
yeah.
So your neighbor is going to know you stole from him. As soon as his car is gone, he's going to look, and you're driving in that same car. He's going to say, dude, you stole my car. He's going to call the police on you. You're going to go to jail, right?
Yeah.
Right.
Where the person out of town, right? Or across several towns, well, you still probably end up going to jail, but you're less likely to go to jail because they're not going to know that you stole their car, right?
Wait, so you go to jail for theft?
Okay, so let me give you the analogy, right? So nonmetals share with other nonmetals, where nonmetals will take away from metals. Metals are like the guys that are across town. So your nonmetals are going to take electrons from them, but they're going to share with their neighbors, right? They're going to share with other nonmetals. Does that make sense? So we talk about H2O, water. You guys have heard of H2O before? Christina, you've heard of H2O before?
Yes.
Okay, so we know that water, right? So we have water. Water it forms what we call a covalent bond. It's sharing of electrons between hydrogen and oxygen. In this case, 2 hydrogen and 1 oxygen, okay? So what's that structure? Oxygen looks like what?
Oh.
Oh, how many valence electrons?
6.
1, 2, 3, 4, 5, 6. We'll do this. Hydrogen. What's the symbol for hydrogen?
H.
H.
Yeah.
Okay. And how many valence electrons does hydrogen have?
1.
1.
Yeah.
Okay. Okay, so hydrogen has one valence electron, and oxygen has 6 valence electrons. So how many electrons, what are the most electrons that hydrogen wants to have around it?
What?
Is it 2?
It's 2, right? Because it wants to be like whom?
Noble gas.
It wants to be like a noble gas, but what noble gas does it want to be like?
Neon.
Does it want to be like neon?
Helium?
It wants to be like helium, because helium has 2 electrons around it.
Yeah.
So that's the closest electron, that's the closest noble gas to it. So it wants to be like that guy, right?
Yeah.
So the most that hydrogen, the most electrons that hydrogen can have around it is 2. So it wants to try to get to the point where it has 2 electrons around it. So it will be just like helium. So if hydrogen and oxygen share these 2 electrons here and share these 2 electrons here, how many electrons will oxygen have?
8.
8.
It would have 8 valence electrons around it. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so isn't that what it needs to be like a noble gas?
Yeah.
Yes. Okay.
Yeah.
So in that case, we draw this structure with a line. This line means that we're sharing 2 electrons. Okay, and everybody's happy. Hydrogen has 2 valence electrons around it. Oxygen has 8 valence electrons around it, and hydrogen has 2 valence electrons around it. So these guys are forming what we call a covalent bond. Okay, covalent means that we're sharing. Okay, you guys with me so far?
Yeah.
Okay, so what about if I have H2? How many valence electrons does hydrogen have?
Sorry, I didn't get that.
If I have H2, how many valence electrons does hydrogen have?
1.
Okay.
It has 1. Okay, so if I have 2 hydrogens that are coming together, what is that structure going to look like?
It's going to be an H and then a line connecting to the other H.
Okay.
Simple?
Not
Sir,
quite.
we have a question.
Yes. Who is that?
How do you know how many electrons, valence electrons, does each element have?
I can show you the quick way, or we can go through using electron configuration. So if we use electron configuration, you just take the core out, and then the number of extra valence electrons would be the number of valence electrons it has. The quick way is we're only going to be looking at the S and the p orbitals. First off, let me explain that. Because these guys are transitional metals, they're kind of special, right? So they're special cases, they're going to have special circumstances that are going to make things much more complicated. But group 1, group 2, group 13, 14, 15, 16, 17, and 18, these guys are well understood. They're always going to behave pretty much the same way all the time, right? So all you would have to do is you want to count the number of electrons. Let's say we're talking about, pick anything that's in any of these groups. Helen, I think that's Helen, right?
Yeah.
Okay, pick a chemical in any of those groups and I'll tell you how to.
Let me see. Because I can see, I would say PO.
PO, this guy down here.
Mm-hmm.
Okay, polonium, right? So if we go polonium, we would go to the 6th period, and then you just count the S and the p orbital till you get to polonium. That's 1, that's 2, that's 3, that's 4, that's 5, that's 6. So you say PO 1, 2, 3, 4, 5, 6. That's the quickest way of doing it.
Okay, I get it now.
Okay.
Okay.
So let's say we had strontium. So what is that going to be?
So that's gonna be 2.
That's right. It's going to be 2. 1, 2. That's it. Simple.
Yes.
Okay. So that is the quickest way of doing it. Okay.
And what happens with the other ones, with the middle one?
Those guys are a hot mess, right? And there's a lot of other things that happen in regards to those guys. And so they're called, part of them, they are called transitional metals. So the fact is that they can actually have more than multiple charges, right? So sometimes there'll be a 2, sometimes there'll be a 4. So it really just depends on who they're working with and in the context that they're working, okay? So those guys are going to be a special case, so we'll handle those a little bit later.
Okay, thank you.
Okay. Okay, so now that you guys are familiar with this, let's say we have O2. How many valence electrons does oxygen have?
6.
It has 6 valence electrons. 1, 2, 3, 4, 5, 6. So if we have 2 of them, they both have 6. 1, 2, 3, 4, 5, 6. So I'm going to tell you how I go through the process of drawing the Lewis structure for compounds, right? And you can use Lewis structures for ionic compounds, and I'll show you that more appropriately afterwards. But it's mainly used for when we're talking about covalent compounds. Okay, so in this context, I count the total of valence electrons. I have 6 here, and I have 6 here. So that's how many? 6 plus 6?
12.
12. So I know that I have 12 electrons to work with. So I'm going to try my best so that everybody reaches its octet. Everyone has 8 around them. Okay, so if I go O, okay, I did this, right? That's 2, 4, 6, 8, 10, 12. This guy has 2, 4, 6 around it. Oh, that doesn't work, does it?
It doesn't.
Okay, so I need to figure out another way to make this work. So let's say, okay, I'm going to draw these here, and I'm going to put these in between the 2. So now they're sharing a total of 4 electrons. Now, when they're sharing 4 electrons, they form what we call a double bond. Okay, so each line represents 2 electrons. So that's 2, 4, 6, 8. So that has 8 around it. That's 2, 4, 6, 8. That has 8 around it. Does that reach the octet rule?
Yeah.
Yes.
It does. Okay, so we can share more than just 2 electrons. We can actually share 4 electrons, or we can share 6 electrons, right? So it just, you want to try to get to the octet rule. Okay, now somebody's going to ask me this, right? Somebody's going to say, Dr. Henry, are there any exceptions, right? And I'm going to say, yes, there are exceptions, and we'll get to that later, Mary.
What?
I'm just sorry, I'm just predicting what you're going to say. Okay.
I wasn't going to say that.
Okay, so now, so I did one for you guys. Now I want you guys to do one for me. Okay, so if I have nitrogen, N2, okay, so what is the first thing that I want to do?
You want to know the valence electrons?
Okay, how many valence electrons does nitrogen have?
I think that's 5.
1, 2, 3, 4, 5. Okay. Times 2. So this one also will have 5. Okay, so then that's a total of 10. So I have 10 electrons I'm working with. Okay. So how can I set this up so that I have 8 around both of them?
Well, they will have to share 3. 6. Oh, yeah.
They have to share 6. Okay,
Yes.
so they're sharing 6 electrons. It'll be like this.
No.
And then shorthand, we'll write it like this, because I hate looking at all those dots. Okay, so that's 2, 4, 6, 8. Okay, that's good. 2, 4, 6, 8 around both of them. So they're both happy, right?
Yeah.
Okay. And then if we count all of the electrons together, that's 2, 4, 6, 8, 10. So that matches up too. So I'm good to go. That's it. Simple. Not too hard. Okay.
Not too hard.
Okay, so those guys, that's called covalent bonds. The fact that they're sharing electrons. Okay. Let me talk a little bit about covalent bonds. Okay. So our compounds, most of our molecular compounds, they're going to be covalent bonds, right? A lot of them will be. Okay. So in the case of, here is an example, our molecule H2, right? That is an example of covalent bonds. They're actually sharing the electrons. Okay. Let's go clear. Okay, so because you're sharing electrons, right? Those electrons aren't free to do whatever they want to do, like in the case of the ionic compounds. So they're not going to conduct electricity. So one thing that we can say about covalent bonded molecules, right, or covalent compounds, they're not going to conduct electricity. So here's an example. We have water, we have sucrose and water, and then we have sodium chloride in water. So the sodium chloride is going to dissociate. You're going to have the plus and the minus charge running around in solution. Because it has that plus and those minus charge, those ions, it's able to conduct electricity. Right? So if we hook it up to a battery, run electricity through it, we're able to get the light will actually shine. In the case of this, excuse me. Okay. Now table sugar, right? Because it's forming a covalent bond, it's sharing electrons. It's not going to be able to conduct electricity. And water alone won't be able to conduct electricity because it's sharing those electrons. Okay, so those electrons are not free to do what they want to do. They're being shared. Does that make sense?
Yeah.
Yep.
Okay, so let me tell you what the sharing really means. So the sharing basically means that you have two, because electrons are always rotating around the nucleus. You guys remember that? We kind of talked about. So we have the nucleus here, then the electrons are always rotating around it and circling around it and all that stuff, right? That's all stuff that we learned in chapter 11, chapters 5 and 11, right? Now, what's happening is that when you're sharing electrons, those clouds, so this is my electron cloud, they're going to overlap with each other. So then the electrons are able to sit there and circle around both of the nuclei. Okay, I'll show you a picture of it in a second. Or one more so than the other in some cases. Okay. So in this case, so you guys can see the electron cloud here. So this is what each one looks like. And then when we put them together to form H2, then the electron is literally circling around both of the nuclei. Okay. Does that make sense?
Yeah.
Okay. So then that allows it to be more stable. Okay. Okay, so diagram representing the valence electrons. So basically here is an, I got carried away. This is supposed to be a question slide. Got carried away and I showed you the answer already. But in the case of F2, right? F2, the way that we would write that is same way. How many valence electrons does fluorine have?
7.
7.
No.
Okay, Helen. So if I have two fluorines, how many electrons are they going to share so that they'll be stable? So it would have 8 around it.
1.
Okay, so it's gonna, each one is gonna share 1. Okay, so then that's 2, 4, 6, 8 around this fluorine. 2, 4, 6, 8 around this fluorine.
Okay.
Okay, are you guys with me?
Yeah.
Good. Okay, so I'm losing my voice here. Okay, so I'm gonna put a couple up here and we'll see what you guys are able to do. So we have CO, we have CO2. I'm gonna show you this one. And then we're gonna have NH3. Okay, so I'm gonna show you the quick way of knowing who's gonna be in the center and who's not. So in the case of CO, excuse me, CO2.
Sorry.
Hold on 1 second. Okay.
Don't die on us, Dr. Henry.
Try not to. Okay, that's better. Okay, so if we look on the periodic table, I'm going to show you the quick way, and then later on we'll get into the nitty-gritty of it. The quick way is, the further you are from being a noble gas, the less you need to be on the ends. So, or we'll say strength-wise. So fluorine is really, really strong because it's really, really close to being a noble gas. Oxygen is really strong because it's only 2 away from being a noble gas. Nitrogen is stronger than carbon because it's 3 away from being a noble gas. Carbon is kind of like, how many of you guys have siblings?
I do.
I do.
Do you guys have more than 1 sibling, or some of you guys have 2 siblings?
I have, well, in total of us, it's 7.
Jesus, wow.
Oh,
That is a big family. So you guys probably experience this more so than anybody else. So when me and my sister used to take road trips with my family, so the way it worked was, until my sisters got old enough and big enough and they could kind of push me around. But in the beginning, I was the oldest, right? And so I would always push my little sister in the middle, right? And my little sister was, you know, she was little in the beginning. And so we'd always push her in the middle, right? And so typically the weak guy always gets put in the middle, right? So do you guys do that too?
yeah. No.
No, you guys don't. You don't put we always put the weakest one always gets pushed in the middle. I'm not sitting in the middle. No,
Okay, I remember I do that. I did that.
Yeah, so we all did that. So that's the same thing that's going to happen here. So you're always
Don't make fun of me, Dr. Henry.
Okay.
I would always be going on the middle, and I still go in the middle.
Yeah, so we know that Alan is the weak guy in the family, right? So in the case, carbon gets to be like Alan, right? And so we're going to put carbon in the middle. And so carbon has 4 valence electrons. Oxygen has how many valence electrons?
6.
1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so that's a total of 6 times 2 plus 4.
16.
Okay, so we have 16 electrons to work with. So we need to arrange these 16 electrons so that everybody reaches its octet. Okay. Pull up our slide again. Okay. So in this case, right now we have 2, 4, 6, 8 around oxygen, but we only have 4 around carbon. So what can we do to kind of make this so it works out?
Can you put double bonds connecting from the oxygen? in the carbon.
So you're saying, so we're going to take these two here, we're going to put those in the middle. And we're going to take these two here, we're going to put those in the middle. So then we get,
No, I don't think that will work.
are you sure? Actually, let me use a
I
different.
think single bonds are okay.
You want to put money on that? So if we use a single bond, right? This is what a single bond. That's 2, 4, 6, 8 around this oxygen. You have
Yeah.
2, 4 around carbon, and then you have 2, 4, 6, 8 around this oxygen. Does that work?
No.
No, because carbon does not have 8 around it.
Yeah.
So if I did this, and I take these 2 electrons from, like, say, the bottom here, and I bring those over, and then I take these 2 electrons and bring those over. So now I have 2, 4, 6, 8 around this guy, and then 2, 4, 6, 8 around this guy, and then 2, 4, 6, 8 around that guy. So everybody's happy. Okay, are you with
So
me?
you kind of like, so you're like kind of sharing. Is that what it's?
Exactly. That's what covalent bonding is. It's sharing. Yes. Yes.
So so each line would be like when you're adding them up, like you have the 2 on, there's
Yeah.
4.
Each line represents 2 electrons.
Okay.
So there's 2 here. That's 4 here. That's 6, and that's 8 around this oxygen. And then here, that's 2, 4, 6, 8 around this carbon. And then here, that's 2, 4, let's say 2, 4, 6, 8 around that oxygen. Does that make sense?
And then you said, yeah, so and then you said what determines what goes in the middle is the one that's farthest away from the
noble gases.
Noble gases. Okay. Yeah, that makes sense. That makes a lot of sense, actually.
Okay, now I should say most of the time. The other thing is hydrogen can never, ever, ever be in the middle. Hydrogen always has to be at an end. Can never be in the middle. Okay? So what I like you guys to do is we'll do this guy. And then, oops, do this right. And we'll do, what is the other one? So we have CO. There's one more, and I can't think of it right now, so you guys are going to get off. Oh, no. I don't know what it was. Okay, so you have these 4 guys. Okay? I know
It's a C with 3 bonds connected to O and then 2 electrons hanging off of each.
Okay, so those electrons hanging off of each, those guys are called lone pairs because there's 2 of them. So we call those guys lone pairs. So those are electrons that are not used for bonding. They're not being used for bonding. Okay. So what about NH3? I saw Tucker working on this one. And Sal, actually.
So it'd be, wait, am I writing it on the?
Yeah, you could write it on my board.
Okay. Let me try to get to.
While you're doing that, we'll have.
Okay, I can write now. So it's going to be 3.
So we have Christina. Can you do me CH4 for methane?
I have a Chromebook, so that would be difficult.
Oh. So do you want to dictate to me what I need to do? And we'll have Sal do HS. So Christina, tell me what I need to do.
Okay, so you put the carbon in the middle.
Okay.
And then connect it all with H with single bonds for each one of them.
Everybody happy? 8 around carbon, 2 around each of the hydrogen. Is this a smiley face, Doctor?
Yes, it
Dr.
is.
Henry.
Yes, it is.
Okay.
Dr. Henry, is hydrogen the only element that just needs 2 valence electrons?
For right now, yes. There's another one that, well, not 2, it's 4 actually. So there are going to be some other weird exceptions here, I promise you, because we got to make it a little more challenging. You know, can't be too easy for you. But yeah, hydrogen is the only one that needs 2 around it. Always will have 2 around it. It will never ever be a center atom. Okay. Sal, are you there?
I am, but this is the one I struggled on.
This is the one you struggled on?
Yeah.
H2S? Okay. Who's going to be in the middle?
The S?
The S. How many valence electrons does it have?
Was it 5? No. 6.
6. Okay, it has 6. And how many does hydrogen have?
Hydrogen has 1.
Okay. So if they each provide 1, looks kind of familiar.
Yeah, makes more sense now. Okay, now I see.
So remember when we told you guys elements that are in the same family or in the same group are going to behave similarly to each other?
Yeah.
Yeah. Make sense?
Yes.
Okay. Simple?
Yes.
Did you solve the CO?
What was that?
Did you do the CO?
It's right here.
I don't get it. I don't
Okay.
understand.
It has how many valence electrons?
That's
Carbon?
4.
That's 4.
Oh,
Oxygen has how many?
6.
1, 2, 3, 4, 5, 6. It has a total of how many?
10.
Okay, so we have 10 electrons to work with. Okay, so all we want to do is try to find a way so that we can sit there and have it so that both have 8 around it. So if I move this guy in the middle, so then that'll be C, 1 bond, that's 2, 4, 6, 8, 10. So that's 10 electrons. But is that 8 around this carbon?
No.
Nope. Is there 8 around this oxygen?
No.
Okay. So we're going to take this guy. We're going to put that guy in the middle. So then we'll have C. Okay. Now that's 2, 4, 6, 8, 10 electrons. Is that 8 around this oxygen?
Nope.
Okay, so we need to keep going, right?
Yeah.
So then we're going to take this guy, put that guy in the middle. So then we're going to end up with this guy, right? So 1, 2. Okay, so that's 2, 4, 6, 8 around this carbon. 2, 4, 6, 8 around this oxygen.
Okay.
Do you see it now?
Yes.
Okay.
Yeah. Thank you.
Piece of cake.
That makes sense.